Now, it's my great pleasure to present Dr. Professor Hugo Bucher. Hello, Professor. Hello, André. Okay, it's working. The sound is working. Now, Professor Hugo Bucher is member of the scientific committee of Free the Bees. He's a geontologist and he works at the Institute of Paleontology and the Museum of the University of Zurich. And his conference will talk about the deep time, a full perspective on current and changes and current and future changes for diversity. Thank you, André, says Professor Buchner. What's the difference between, what's the link between bees and paleontology? Well, we could wonder, but how could the study of the past tell us about the future if things go well? It may help if things worsen. And then something that is dear to my heart, you see on the side of the screen, the interior of a bee habitat. And this is due to you see that the bees have made a ball on a cross that was in the bottom, and then they started building from the bottom up. And this was in a trunk. And usually when you're in a trunk, the rays are parallel, but here the combs are parallel, but here they aren't. And there's a north-south orientation, but you see complications that they were strayed. And this is typical of the dynamics of the system. And to understand how a system works, we should disturb the system to see how it reacts. And this is exactly what we're going to do, but in deep time with the carbon cycle, which is quite linked to climate, and it will influence biodiversity. And the biomass, the biodiversity, and especially the biomass will influence the carbon cycle and the climate. So now let's go to next slide. I would just like to give you a brief reminder. You see the age of the Earth here, and if you go, if you like in a clockward, then you see the most recent times, and the different colors show when life appeared. For instance, 4 billion years ago, when photosynthesis appeared and everything. So you see that the fossil registers that we have organs fossilized, it's the last 542 last million years. So it's just part of the history of life. When you see the carbon cycle, the temperature curve of the system at the surface of the Earth, we see that by the end of the blue area, we see that the carbon cycle is huge, and it takes place along glaciations all over the surface of the Earth. And then animals appeared, as you see on this circle in green. The earth plants appeared later at the middle of the Paleozoic, and the appearance of earth plants modified the composition of the atmosphere, and therefore the evolution of life on continents. What we're going to look at today, we'll actually discuss mass extinctions. These are rare events in the last 542 million years, but these elements had a huge impact on the life evolution. And maybe without such mass extinctions, without this massive loss of diversity, the total of species on Earth would be who exist on Earth would be much less. So actually, these extinctions catalyze are catalyzers for the evolution. So on this diagram in the bottom, you have the time. Here we start more or less with the appearance of the fossil records and the explosion of the Cambria, and all the phyla are setting up. And then when you take the curve above, which shows the total of the diversity of families throughout time, you see that we reach a plateau, what we call the Paleozoic plateau, with two main interruptions, with losses of around 50% of types and very severe reductions of families. This plateau stops 250 million years ago with the Permian Triassic event, and this is a record mass extinction, and we estimate between 80 and 90% of loss of the marine species. And again, these are families, the number of families, right? These are not the species we're talking about. And after this Permian Triassic limit of 250 million years, diversity has kept increasing even in spite of the fact that at the Cretaceous Paleogene event, we still have a mass extinction. There's another one here, not so far from the Permian Triassic line. I'm talking about the Triassic-Jurassic line. And again, there's an extinction. And what's shocking is that the regime changes after the Permian Triassic event 250 million years ago, and then diversity increases substantially, in spite of the fact that there are still interruptions. And due to both mass extinctions, we consider that a mass extinction is when we have a loss of over 50% of a species. This is for the general framework, and we will discuss this Permian Triassic limit 250 million years ago. So the mass extinction is not something new. It's something that comes back very strongly. And in a famous book, the speech on revolutions at the surface of the globe, Mr. Cuvillier had understood that along life history, species disappeared, and not in a random way, but per packages. So at a set time. And since 20 years ago, the study of mass extinctions has started again with a great attention on behalf of researchers, essentially given the man action at the surface of the Earth that could lead to a sixth mass extinction. So here, a few years ago, we had a special exhibition on mass extinctions in Zurich. You have the cover here, and here the link that enables you to download the whole content of the catalog of the exhibition. So I won't go over it, but because you have the link here that enables you to update yourself, even though it's not quite updated because it's 10 years old, but still. So it's on mass extinction. So these mass extinctions, had they not existed, we wouldn't have had an increase of diversity, and especially this Permian Triassic line has led to creation of different species, and biodiversity, instead of staying in a plateau, has gone up and up and up. Now, what are from a geological viewpoint, what are the potential causes of such mass extinctions? Here on this diagram by Vincent Propriot, who is still who is considered as a climate skeptical, even though he's not skeptical concerning the climate. He says that not everything is based on CO2. No, he thinks that we should see the sun activity and how the sun activity influences climate. To his viewpoint, climate doesn't just depend on CO2, but on sun activity. Of course, sun activity is on a greater scale than the one that interests us here. So CO2 is studied in shorter scales than the sun activity. So that's why I think that he's not a climate skeptical, as some call him. So on this diagram, we have the main extinctions, and on this is on the X on the X line, and on the Y line, the time. We see the yellow spots, which are bigger or smaller, depending on how big or small the mass extinction takes place. And here you have an arrow with an important yellow dot. And these are what we call the main volcanic provinces, the giant volcanic provinces. What is it? What is it? Well, volcanic events that are measured in million square cubic kilometers of basalt at the surface of the Earth. And such correlation here is almost perfect between the presence of such giant volcanic provinces and the mass extinction events. Now, another distinction. If million of cubic meters of basalt arrive at the surface of a continent, so in the open air, all products of gas extraction of such magma go into the atmosphere and have a huge impact. On the other hand, if the eruption is underwater, then the marine column will protect the full environment of volatile products and chemical products that are extruded by such basalts. So all in all, such correlation is striking. It works well. And if we want to compare the past and our current period, in the past, it was volcanic eruptions that are measured in million and million cubic meters. When they arrive to the open air, they lead to a mass extinction. And if it's underwater, the effects are less and they don't lead to mass extinction, or the extinction is average or medium. Now, what's the mechanism behind such volcanic provinces? Here you have a cut of the earth, and you see the cut that's very unstable. You have thermic anomalies, and if they're too strong, they will go under the earth coat, and it ends as a mushroom shape here. And it takes time for the whole mushroom to go through the coat. And under it, you have semi-rigid plates that can move in the tectonic plate. And once the mushroom arrives through the lithospheric plate, this plate will heat, and then the magma will go through it, will cook anything that's in it, and they will set up, or they will develop plateau, what we call plateau basalts. And the lithospheric plate still moves. The plate doesn't stop moving when the mushroom or the plume starts moving. You see that here the basalt of the plateau that's here and the mantle, but the tail of the plume is active. So behind these float basalts, you see a passive marker of the movement of the plate under the mantle. So the deep mechanism is purely earthly, and it has to do with the heat instability in the frontier or in the transition region between the core and the mantle. Of course, fortunately, we don't have such hotspots every day because it would be unlivable. Now, how are they scattered in the current geography? Here on this map, you see all the main volcanic provinces that geologists acknowledge today. For instance, concerning the end of the dinosaurs, the Tertiary Cretaceous, you see that it covers half of India, and it came out at the time of the dinosaur extinction. At the time, India was not in that position. It was above the Reunion Island. And in the Reunion is where the hot spot is. This is where the tail of the plume is still active. The Reunion is still an active volcanic region. And in the south of India, you see the main volcanic province, which is still active with its million cubic kilometers of basalt. Iceland is also a hotspot, and you'll find the rest of such volcanic province here in the North Atlantic, along Greenland, and in the Eastern Atlantic here. We could multiply examples. Maybe one last example, which is interesting, is the one that's here on the right hand. I'm talking about the great volcanic province, Hong Kong and Java. It's a underwater province, maybe one of the greatest we know, but it didn't lead to any mass extinction. Why? Because it was an underwater. It was underwater. So all in all, this is the the suspect that's easy to find concerning mass extinction causes. Now, let me go back to this slide to show you the Siberian traps. And these are the ones that coincide with a great mass extinction that took place 250 million years ago. Now, on the map, you see the extension, the maximum extension of these Siberian traps. It's absolutely gigantic. It goes from the Kerala Sea to Central Asia. And from a volume viewpoint, we think that it's 5 million cubic kilometers in this province. And it's the least we have calculated. Why? Because most doesn't come to the surface. Most of it is subsurface. And we only reached it by drillings. And we can't drill everywhere. So this is just the least value we could find. And we have radioisotopic measurements on these flows that came up to surface, and that took place less than 1 million years ago. It's probably, 1 million years is and 5 million cubic kilometers maybe appeared 500 of 600,000 years ago. And what did it bring to the atmosphere? Well, steam, and then a lot of carbon dioxide this carbon dioxide may come from several sources. It may be purely volcanic, mantellique, so coming from the mantle, or it may contain all combustion products from the geological tiers, which that comes from the magma that cook everything on their flow. For instance, North Siberia has most of the coal veins in the world. It's basalt, and this coal was cooked by the basalt that came up, and it adds methane in the atmosphere. And methane is much more than CO2. It's a house warming gas, a greenhouse gas, much more than carbon. And then you'll have other things that come out with it at the same time: hydrogen, chlor, fluor, and mercury. Mercury is also a chemical marker of the volcanic activity. And here we find anomalies in mercury concentration in the sediments that ended up in such volcanic provinces. So these volcanic provinces bring a whole series of greenhouse gas and pollutants, which are quite stressful for life. Submetal, I'm talking about submetals, and it depends on the rates of injection, so the amount per time unit. For instance, if in every basalt flow, which is quite clear on this photograph, if each time you have another amount of such toxic products injected in the atmosphere, and the biosphere has no time to recover between both events, then you get to no return point and everything may collapse. Because the atmosphere can't compensate because it goes too fast for it. So how can we compare past and present? How did it happen in the past? Well, here you have these veins that are set up in these great volcanic provinces. And right now we have the anthropogenic activity, industrial activity, that could be the equivalent of such great volcanic provinces that took place in the past. And again, what is important is that these eruptions are sub-air, which is important for anthropogenic activity, because if it's underwater, all these greenhouse gases and toxic products will not spread around the earth. Now, this is a temperature curve in our system. This is what we call the carbon cycle. I think that most of you are familiar with it, but still, we need to do a little reminder. Why this diagram? Well, it is cut in two, and in the upper part we see the fast cycle, what we call the fast cycle, and in the lower part the slower cycle. Most of you are familiar with fast cycle, and in the terrestrial formation, what is it? For photosynthesis, plants will consume CO2 and plants will breathe. If they're not doing photosynthesis, they breathe and they spit CO2, and this way the circle goes around between the earth and the atmosphere. But now it's not as simple as that, because part of the carbon, which is stocked in the terrestrial mass, goes into the ground, and when such carbon goes deep into the ground, it may go to the long cycle, and in the long cycle we need to wait million or 10 million years before such carbon comes back to the surface of the earth and plays a role in the life cycle of carbon. So it's a way out for carbon where it is stocked in the rocks. It may make coal and in gigatons, we estimate that the total amount of carbon in terrestrial rocks or underwater is around 70 million gigatons, and may vary. It may go from 50 to 70,000 gigatons of carbon, of coal. Now let's look at the carbon undersea. The primary producers are phytoplankton. So they are these microscopical weeds that consume CO2 and that through oxygen. So instead of terrestrial plants, we have phytoplankton, but we have a cycle of consumption and production of CO2, which is the same. So what's the common link between the sea and earth? Above all is what's above it all, atmosphere. There is no marine atmosphere or terrestrial atmosphere. It's a common reservation for earth and sea. Now, in the sea, such primary producers will be consumed by primary consumers, and we go up the project scale, but all the carbon stocked in such organic material, which will not go in the short cycle. It will be a particle in the sediment that can give either carbonated rocks, for instance, with the debris of organs. For instance, you may have shells or corals, and many sea animals that produce carbonate skeletons. So they take part of the carbon, they trap part of the carbon. They are kind of a phyto buffer. And when the shells are destroyed, they lead to produce carbonated rocks. And this is a huge reservoir of carbon. Part of it can also transform under very specific conditions and quite rare, geologically speaking, in oil, in petrol, and in gas, in oil and gas. And we see the geological conditions that may lead to gas and oil. We think it's a bit of a pity to burn it in combustion engines, and we should keep it for chemistry. And we see that life here plays a great role. Here you have, and it's represented here in the terrestrial space, the volcanic activity. You have pollution either from geological reasons, natural pollution coming from volcanoes, for instance, or the current anthropogenic activity. Now, where do we look for information concerning this greater mass extinction 252 million years ago? Well, in such a geography, here you have the plate limits, the continents, and you see the oceanic rhythms where the new lithosphere is formed and basalts go up. And these are small volcanoes compared with volcanic provinces. And then you have the oceanic lithosphere, which is longer than the Earth one, and it melts and it gives a volcano chains like in Japan and the fire belt in the Pacific, and it continues in the US, Central America, and South America. Now, this is the current position. Now, let's see if we want to put things into perspective. What are the positions of sediment basins that we draw our data from for what happened 250 million years ago? Well, you see here, there's a geography which is totally different. Actually, we just have one hypercontinent that we call Pangaea. We have a huge Pacific Ocean, which we can call the Paleo-Pacific. And then here, kind of what we call the tethys, with blocks here in this tethys. Such blocks come from the south edge or the north edge of the south supercontinent of the Pangaea. Such blocks have oceanic grids that are born, and they cut off this edge and such oceanic areas are greater, and they push away the fragments of continent that were at the north of such ridge. So they push them, and all this plate here migrates up north, and all these little fragments that are cut off migrate to the north and collide with Eurasia. And this is the explanation of alpine chains from Europe all the way through Asia. So this is the geographical context of the time, and the altitude is quite important. There's a crucial spot on which we don't have too many data here. It's what we call the Amrit Shelf in Australia. This is where, when we want to detect climate changes, it's easier to detect them when one is near the poles of the time than one is closer to the equator of the time. So this is concerning the paleogeographic context. Now, what happened with nekton? What's nekton? These are active animals that live in the water column, and the mobile animals that are active and who live in the water column. A simple example here, ammonites, cephalopods. They're quite capable of moving horizontally and vertically in the water column, and they're cephalopods, so they're mollusks. But ecologically, they're closer to fish than gastropod. So if we look throughout time, here you have the time scale in million years with systems, etc. Now, if you take the curve of full diversity of such ammonites, you see that in the tertiary they increase. Now here they suffer a first decrease at the end of the Capitanian, and this is due to a volcanic province, but much lesser than the one of the Permian Trias. And we see that they go up a bit there, and then it drops. And then when we get to the Trias, very soon, in a few million years, the diversity of this ammonite grows hugely. And then we have oscillations that will reach a plateau and then drop again. And once we reach the Trias-Jurassic event, a new volcanic province is developing. Now, we see here that the extinction of ammonites has almost led to their disappearance, to their full disappearance. But what happened later was that, given the fact that all ecological competitors of ammonites had disappeared and a few of them had survived, well, they could get back to all free niches, and this led to a huge increase of diversity. And in red, you see an additional point, and this shows what happens here after the mass extinction. We see that here there's a zigzag. And at the late Smithian, which is a stage of the inferior Trias, so after the main extinctions, we have additional extinctions. And this one was even more severe than the end of Trias extinction. So same for nekton. So here we see groups of organs that are organisms that are very affected, or bodies that are very affected, not just by main episodes of extinction, but also in the 5 later million years, there's other added extinctions. And this is what we're going to try to understand. This is why the recovery after such extinction was very long, because there's not just one extinction, but a succession of extinctions in an interval of 5 million years. So on this diagram, you see on the very left, the ecological column. This is what we see on the field with different tiers, and each colored bar represents the areas of ammonites. This is our chronology concerning the evolution of ammonites. And here you see that they represent 5 million years. It represents 5 million years, and you see the main amount of, here you see the amount of different fauna of ammonites that have succeeded each other, and it's colossal. And we have time intervals in these 5 million years where the life cycle of species is not bigger than 1,000 years. Now, carbon is a good indicator of the global full balance of the carbon. We see that there are huge fluctuations or huge differences, and then they will stabilize at the end of inferior Trias. After 5 million years, they stabilize, and that's where when the sea animals get again a comparable diversity with the first wave of the extinction. Now we can reform temperatures by measuring the isotopic composition of oxygen on teeth, fish teeth, or microvertebrated teeth, and such phosphate, this animal conserves keeps the isotope of the sea of the time, and it enables us to develop the temperature evolution of the surface. And this is what we did 10 million years ago. And at the time, we were shocked because of that spot here. This dot was actually wrong, and it's much here. It's more here. So it's closer to oxygen isotope values, so colder values. So here at this Smoothian-Spassian limit, as we call it technically, the ammonite extinction was greater than in the Trias time, and this is what matters for these nectons. And here we see that temperature more or less resembles the fluctuations of atmospheric pressure of CO2 and temperatures. So all in all, there's a correlation which is relatively gross between the variation of CO2 pressure and the temperature of the sea water. Now, another diagram, smaller diagrams inserted in such bigger diagrams based on the timeline. So here you have the ages, the absolute ages, calibrated in million years. And here, for instance, there's rates of renewal for ammonites during that time. And here you see a peak. So this renewal corresponds with extinction rates and appearance rates that are very high. So you produce a lot of species, but with very short life cycles. So the evolution here is in carousel mode. So there's a lot of species of very short life cycle that follow each other. And here you have a maximum of atmospheric pressure of CO2 in the atmosphere and maximum temperature. So here you see that a higher temperature, this is the highest temperature for inferior Trias. And what does it indicate for ammites? It doesn't show an extinction. On the contrary, it indicates crazy renewal cycles with very short life cycles, but that succeed each other very fast. Now, extinction comes with cold, and such cold induced probably glaciation. So waters were stuck in ice on the continents, and to vary the sea level, there must have been a regression of 100 meters. The sea level went down about 100 meters, and to have such a low sea level, you take the water, you separate it from salt, and you place it on the continents as in form of permafrost in ice. So the real catastrophe here, one of the main catastrophes that followed the main episode linked to the implementation of the volcanic province, doesn't take place during the higher temperatures, but during the lowest temperatures. And lowest temperatures lead to a regression, a full regression. What does it mean? Well, what did it cause? The exudation of continental plateaus. Most marine diversity is concentrated here. So everything that's on continental plateaus is reduced to a very thin fringe. And if you destroy the habitats of the species, then you will generate a quite ferocious extinction. Now, if we look at plants, it's the column here. Here you see that thanks to the pollen we find in sediments, we may distinguish between humid climates and dry climates. During the highest temperature here, plants are in a very humid climate, and during regression, the climate is very dry. Now, as time is running short, I'm going to go a bit faster. Now, the key to understand all this with carbon cycle are the dates we may set. For South China, here's the succession of the 5 million years that covers the inferior Trias. Then you have carbon variations and all different date points that enable us to get this original form of the signals. Here you see in the recording, which is not retro deformed, we see great cycles shown by carbon isotopes. And if you stretch all this for dates, then you get something of the like. It's this green curve here with our three main cycles. This one we're still studying and calibrating. But here you have the setup of the volcanic province, the development of the volcanic province, which is a kind of buffer that will takes the carbon cycle that was under 4 per 1,000, that was before the development of the volcanic province that was 4 per 1,000. So you take the carbon cycle out of its balance and you get gigantic oscillations that will take 5 to 6 million years to be fully compensated. Now we try to see how long it will lead to trouble. We see it on this diagram. You have the isotopic line vertically and the timeline horizontally. Let's take the main tier T. You do a volcanic injection here during 100,000 years and you inject 6, 10 power 18 mold of carbon in the atmosphere. You get a negative response and then you get a positive reaction, and then this gives something like between 200 and 300, between 2,000 and 3,000 kilo per year, 3 million years to stabilize. So based on the time of such eruptions or the amount of carbons injected, the response is different. But what's the same feature in all responses? When you only consider the CO2 injection in atmosphere, you see a great asymmetry between the negative shift and the positive one. The negative is very short and the positive is very long. So it doesn't correspond here with what we have, because here we do see a CO2 injection of volcanic origin, but then we have these cycles and they're perfectly symmetric and they may not correspond to a volcanic origin then. if we had a volcanic origin in the cycle, if we had, when we have negative values here, so when the atmospheric pressure is highest here, then we should have traces of mercury, but we don't find any, or we find them, but not set on these time traces, and they're just due to local mechanisms and not for global ones. So the only volcanic episode that leads to this province, the carbon cycle is unbalanced and it goes to an instability period. Now, such oscillation of the carbon cycle after carbon hydrocarbon extraction. Do we have, does the tail of the plume still throws this? Well, no, because we don't have the same rediversification. And the nekton, during the lesser temperatures, there's an extinction of them. So during lesser temperatures, there's extinction of nektons, and during highest temperature, the nektons appear again. Now, astronomical control of the climate on the Earth. Quaternary glaciations are due to the interaction of the different planets of the solar system here to get climatic cycles of between 1 to 4 million years. What will regulate this is in the interaction between the Earth and Mars, which controls the ellipses of the Earth. If we have astronomical cycles of astronomic origin, then we should have constant. Here you see that signal increases here. There's 1.2 million years, 1.6, 1. So it cannot be a control of astronomic origin. And third hypothesis, which is the one we favor since little time, at least in my group, it would be a nonlinear response of a cycle of the sea excitable, the excitable sea. And what should we add to this? To the modulation of the amplitude, the modulation of the amplitude through the biomass. And what's interesting here is that before the movement, we have a balance, and after, once everything is calm, we have reached a new equilibrium point of 1 per 2000. So here you're at 4 per 1,000, and here you are at 2 per 1,000. So if we had no biomass, the first trouble would be the strongest, and the signal would be less. So the amplitude should be less, but it's not what happens. We see the period increases and the amplitude is maximum here. It is higher at the beginning and then it diminishes afterwards. So this is strongly indicating that, this strongly indicates that apart from a nonlinear cycle of the carbon, we need to introduce a retraction line, which is only the biomass, which is kind of like a buffer of the carbon cycle limits. And this takes us to conclude that what is an attractor basin? It's before the variation, which is more than 4 per 1,000, and then we get to 2 per 1,000, and there's oscillation between the two. If you have a topographic surface like this one with two basins, you have here a ball, right? That's in the bottom. And if the ball moves a bit, it will not go too far. It will come back to the balance and the bottom of the basin. But if the movement is greater, it may go out of the basin and it may fall in another basin around a new balance here that will be different. Of course, the amplitude of the basin may be variable, And the fact, how can you go from one basin to another? Well, it depends essentially on the intensity of the disruption, the disturbance of the system, and how we will, and the intensity and the rib. And here is the same thing in three dimensions. Here's what we call a basin. And in the dotted line, we have the tipping points. Once the point that represents the stage of the system reaches this line, it will fall. And it will not fall straight ahead, because the system will get into another attractor line. So it will draw oscillations as the ones we see if we didn't have the place that concludes all this. So to conclude, excuse me for displacing the plan. And as a conclusion, briefly, we can see a similarity between the CO2 and temperatures. It's not perfect, but it works pretty well. Our model works pretty well. Excuse me, if I could just end my conclusion. I don't know what's happening, Hugo. Can you try just with the sound? Oh, okay. I don't know why. This is a bug. Anyway, I'll end with the last link. I will read conclusions. The initial disruption of the system leads to the great volcanic presence. And then what we're doing, and the whole community is doing, we compare the CO2 extraction rates previously and currently. So what about the rate of CO2 production? Are they comparable, the ones that we do now with the ones in the past? The answers will be found in the rate of cycle changes of carbon. The tip points, when will be override when the biomass is insufficient to compensate disruption. So, what is the tip point in the past and currently? This is still an open question. Now, what we can show with certainty is that once we reach the tip point, the carbon and climate cycle would vary extremely over several million years in a non-linear dynamics before we stabilized once biomass is restored. So when we reach this tip point where we're not facing one catastrophe, but a series of catastrophe, and the origin is not volcanic. It is just that the whole system was disrupted, and this disrupted system is not able to get back to its initial state. Why? Because the biomass is not there to slower its anthropogenic or volcanic variation. So what does it mean? The more we destroy natural habitat, the more oscillations that could lead, that could reach the tip point are there. And the higher the temperature, it is not bad for plants, but it is bad for their ecology. When we have high temperatures, we see that ferns are everywhere, and they are like cockroaches with regards to plants. And then when temperatures go down, other plants come back. Now in sea, these higher temperatures lead to extinctions, especially of nectons, and then very short life cycle species will be developed. Now, when temperatures are down, it leads to glaciation, and this is what leads to catastrophes in the sea. and the extinctions are greater than when the volcanic province is developed, but terrestrial means are less disrupted. So this is what may expect us if these tip points were to be reached. Thank you for your attention. Thank you, Professor Bucher. Thank you for your contribution in this day. Now, I propose that we come back at 10 past 10 to listen to the next speaker. Thank you.